A magnitude 7.4 earthquake just tore through Colombia. Buildings are down, airports are closed, a volcano started erupting hours later. And within minutes of the shaking stopping, people online were already saying, "I called this, so let's get straight into it." Did anyone actually predict this? Could anyone have? And what's really true about earthquake prediction? Not the version that sounds exciting on a live stream, but the version backed by actual seismology? That's the video. No stalling, no waiting 10 minutes for the good part. Let's go. Early morning, local time, a magnitude 7.4 earthquake struck Colombia. The depth is the single most important number in this entire story. So remember it. Roughly 110 kilometers down, that's not a shallow crustal quake. That's an intermediate depth event happening inside the slab of oceanic crust that's subducting underneath South America along the Pacific coast. Why does depth matter this much? Because earthquake damage isn't just a function of magnitude. It's a function of how much of that energy actually reaches the surface and how concentrated it is when it gets there. A magnitude 7.4 at 10 kilometers. Depth, centered under a major city, is catastrophic in a very different way than a 7.4 at 110 kilometers. The deeper quake spreads its energy over a much wider area, but with less peak intensity at any single point. That's part of why we saw strong to severe shaking reported across a huge swath of western Colombia, Cali, Pereira, Manizales, and beyond, rather than one city being flattened while its neighbors were untouched. The mechanism was mostly strike slip with a component of reverse thrust, what seismologists call oblique slip faulting. In plain terms, the two sides of the fault mostly slid past each other horizontally, but there was also some compression, some upward thrusting motion layered in. That combination tends to produce more shaking than pure strike slip alone, because thrust motion is generally more efficient at generating strong ground acceleration. Within hours, Colombian authorities had confirmed dozens of deaths, with that number climbing fast as reports came in from harder hit, lower resource areas near the epicenter. Multiple airports suspended operations, some for earthquake damage. At least one because a nearby volcano started venting ash almost immediately after the shaking. Videos showed buildings swaying into resonance and eventually collapsing, sometimes minutes after the worst of the shaking had already passed, which is its own important lesson we'll come back to. This came about 6 weeks after a widely discussed earthquake doublet in Venezuela, two large quakes, magnitude 7.2 and 7.5, striking in close succession, and about 3 weeks after magnitude 7.3 off the coast of Mexico. 3 major magnitude 7 plus events, all touching the broader Caribbean plate region inside of 2 months. That clustering is real. It's documented. It's not in dispute. The question is what it means, and that's where things start to split into two very different conversations. What mainstream seismology says stress transfer can and can't tell us, and what a growing corner of the internet claims it can predict from that same data. Before the dust had even settled, clips were circulating of a forecaster, a self-described geophysicist with a large online following, pointing back to a live stream from mid to late June. In that earlier stream, recorded the same day as the Venezuela. A doublet, he told his audience that Colombia could be next within a couple of months, citing historical earthquake sequences where Venezuela and Colombia seemed to trade off large quakes within months of each other. 6 weeks later, Colombia got hit. To his audience, that reads as a direct hit, a successful, specific forecast that came true almost exactly as described. It's worth taking that claim seriously enough to actually examine it, instead of just dismissing it, because if someone genuinely has a working method for predicting where and when major earthquakes will strike, that is one of the most important scientific breakthroughs in the history of natural hazards research. It would save an enormous number of lives. So let's actually look at what the claim is, and what it would take for it to hold up. The forecast was, Colombia could be next within a couple of months. Not a specific date, not a specific magnitude, not a specific location within Colombia. A country of over 45 million people, spanning multiple active fault systems, and a subduction zone thousands of kilometers long. Colombia, sometime in the next couple months, big earthquake, is a forecast, with an enormous margin for being called correct. Here's why that matters. Colombia is one of the most seismically active countries on Earth. It sits directly on the boundary where the Nazca Plate subducts beneath the South American plate. Plus, it has the Caribbean plate interacting from the north. Historically, Colombia experiences a magnitude 6.5 or larger earthquake rough, lie every few years, and smaller significant quakes far more often than that. Saying a big earthquake will probably hit Colombia sometime in the next several months is a bit like a meteorologist in Florida predicting a hurricane will probably hit the Gulf Coast sometime this summer. It's not nothing, but it's also not the kind of precise, falsifiable prediction that would represent a scientific breakthrough. This is the core problem with evaluating claims like this after the fact. Broad, vague, high probability forecasts over long time windows and large geographic areas are almost guaranteed to eventually come true somewhere, simply because seismically active regions produce earthquakes regularly. If you make enough loosely bounded predictions across enough active ZO, Venezuela, Colombia, Mexico, California, Central America, Japan, Indonesia, some of them are going to line up with real events purely by the base rate of how often these places have earthquakes. That's not evidence of a working predictive model. That's how probability works when your predictions are broad enough. None of this means the person is acting in bad faith. It's entirely possible to genuinely believe your own framework works when what's actually happening is a mix of real geophysical correlation, confirmation bias, and the sheer statistical inevitability of large earthquakes in an active region eventually happening somewhere nearby. That's a very human pattern, and it shows up constantly, not just in earthquake forecasting, but in a lot of pattern-based prediction across many fields. So now let's actually get into the mechanisms being cited one at a time and separate what's real seismology from what isn't. Let's start with what's genuinely legitimate science, because there is some here, and it deserves credit. Earthquakes really can influence the probability of future earthquakes on nearby faults. This is called stress transfer, and it's a well-established peer-reviewed field W within seismology, often studied using something called Coulomb stress modeling. When a fault ruptures, it doesn't just release energy, it physically shifts the crust around it. That shift changes the stress state on nearby faults. Some FOW, LTS get pushed closer to failure. Others actually get relieved of stress and pushed further from failure. It depends entirely on the geometry, the orientation, the dip, the distance, the specific mechanics of both the triggering fault and the receiving fault. This is real, it's measurable, and it's been used to explain documented aftershock sequences and, in some cases, subsequent large earthquakes on connected fault systems. The North Anatolian Fault in Turkey is a textbook example where a sequence of large earthquakes appeared to walk along the fault over decades as each rupture loaded stress onto the next unbroken segment. But, and this is the critical distinction, that kind of modeling requires detailed knowledge of specific fault geometry, rupture area, slip distribution, and the exact orientation of the receiving fault relative to the stress change. It produces a probability shift, not a predictive on. It might tell researchers that a specific named fault segment now has a modestly elevated chance of rupturing over the following years. Not that a country will be hit within 2 months, and not by simply eyeballing that 2 earthquakes happened a few weeks apart in the same general region of a map. Distance also matters enormously, and this is where a lot of the more sweeping claims fall apart. Static stress transfer of the kind that shows measurable causally linked effects generally operates over distances comparable to the rupture length of the triggering earthquake, often tends to a couple hundred kilometers for a large quake, not thousands of kilometers across separate countries and separate plate boundaries. Venezuela to Colombia is plausible as a regional stress interaction, given they share tectonic boundaries. Venezuela influencing Mexico, or a Caribbean quake influencing California, is a much bigger stretch, because you're talking about entirely different plate systems separated by enormous distances, with no established physical mechanism connecting them at that scale. So, real phenomenon, real science, genuinely useful for probabilistic hazard assessment, and also very easy to overstate by drawing a big circle around half a continent and saying it's all connected without doing the actual physics. Now, for the parts of this forecasting framework that go well beyond what stress transfer research actually supports, take the claim about the moon crossing plate boundaries. The idea is that when the moon's position, tracked across a map of Earth, appears to cross over a tectonic plate boundary that increases the likelihood of an earthquake at that moment. This confuses 2 very different things: tidal forces and a 2-dimensional map prodigy. TN. The moon does exert real tidal stress on the solid Earth. This is measurable and studied. But that stress is a function of the moon's actual gravitational geometry relative to Earth's rotation and orbit, not whatever plate boundary happens to be underneath a line drawn on a flat map at a given moment. Multiple studies have looked for a correlation between lunar and solar tidal stress and the timing of large earthquakes, and the results are, at best, weak and inconsistent. Some very shallow, thin crust, near-surface events show marginal tidal correlation. Large earthquakes generally don't show a reliable pattern. The moon was over the plate boundary when it happened is a coincidence being treated as a mechanism. Then there's the idea of antipodal earthquakes, the notion that a big earthquake tends to be followed by a reciprocal earthquake near its antipode, the point on the exact opposite side of the globe. That isn't an established seismological principle. Seismic waves absolutely do travel through and around the entire planet, and they do focus somewhat at the antipodal point due to geometry. The is real wave physics, well understood. and used constructively in seismology to study Earth's deep interior. But focused wave energy passing through a point is nowhere near the same thing as that point being measurably more likely to rupture its own independent fault system as a result. The literature doesn't support antipodal triggering of major earthquakes as a reliable predictive pattern. It's an appealing idea because it sounds physically intuitive, but appealing and validated are different things. Geomagnetic storms loading faults is another one. This is a real area of legitimate scientific inquiry. The question of whether solar activity, geomagnetic storms, or electromagnetic phenomena have any influence on seismicity has been studied seriously by real researchers. But the honest state of that research, even from the papers that report an effect, is that any relationship is subtle, statistically weak, and far from established as causal. It has not reached the point where it's usable for actionable prediction, and mainstream seismological agencies do not incorporate it into hazard forecasting because it hasn't cleared the bar of Lee, reproducible evidence, citing, "We had 2 geomagnetic storms before this earthquake," while also saying, "I'm not saying this caused it," is doing a lot of work. It lets the correlation imply causation in the audience's mind without the claim ever having to be defended as one. And then there's historical date and number pattern matching, pulling out that Colombia had quakes in 1917, 1967, 1991, 2004, noting some occurred in similar months to other regional events, and treating that as a forecasting signal. That's a classic case of a very human cognitive bias, pattern recognition operating on a DA. TASE-IT that's both small and noisy. Colombia has enough historical seismicity that you can find some temporal clustering with almost any neighboring country's earthquake history if you're motivated to look for it. This is different from a rigorous, slide-tested statistical model that's been checked against false positives, moments where the pattern should have predicted an earthquake and nothing happened. Without that check, you're only ever seeing the hits, never counting the misses, and that's exactly how apparent patterns get manufactured out of essentially random noise. None of these ideas are being presented as fringe theories to the audience. They're presented with confident, technical-sounding language. Moment tensor solutions, strike and dip figures, USGS introspective maps. Real tools of real seismology, used as a visual backdrop for claims, those tools don't actually support. That's worth naming plainly, because it's the exact thing that makes this kind of content persuasive. A genuine data wrapped around a set of unproven conclusions. Here's the part that tends to get buried. The official scientific position on earthquake prediction isn't a cover-up. It's stated plainly, repeatedly, and publicly by the U.S. Geological Survey and every major seismological body in the world. Neither USGS nor any other scientific institution has not know how, and they don't expect to know how in the foreseeable future. That is their actual published position, not a hidden one. It's on their public-facing website, in plain language, specifically because they field so many claims like the ones we just went through and want the public to understand where the real science actually stands. What USGS and seismologists can do, and this is genuinely important and genuinely different from prediction, is produce long-term probabilistic hazard forecasts. These say things like, there's roughly a 70% chance of a magnitude 6, 7 or greater earthquake in a given active region over the next 30 years. That's built from decades of data on fault slip rates, historical recurrence intervals, paleoseismology, and stress modeling. It's useful for building codes in insurance, infrastructure planning, and household preparedness. It is not a prediction of when, where exactly, or at what magnitude a specific earthquake will strike next Tuesday, next month, or even next year. The reason short-term prediction hasn't worked, despite over a century of serious effort by very smart researchers who would love nothing more than to solve it, is that earthquakes appear to be, as far as current science can tell, fundamentally difficult to predict at that level of PR. Precision. Faults accumulate stress over long periods, but the exact moment and location a fault fails seems to depend on small-scale conditions, deep underground, that we currently cannot observe directly or measure with enough precision in real time across the entire length of every fault on Earth. This isn't for lack of trying. Countries have poured enormous research funding into it, famously including a major, well-funded prediction program in China in the 1970s that had some limited apparent early success, and then catastrophically failed to anticipate the devastating 1976 Tangshan earthquake, which killed hundreds of thousands of people. That failure, among others, is part of why the scientific consensus shifted hard toward reliable short-term prediction is not currently achievable, rather than being an area actively suppressed or hidden. So when a forecaster says the official agencies are lying, or simply refusing to issue warnings out of institutional indifference, that's a claim worth sitting with honestly. The far more supported explanation is that these agencies don't issue specific short-term warnings because they don't a scientifically validated method to generate one, and issuing false alarms or missing real ones based on unproven methods would itself cause serious harm, panic, wasted evacuation resources, and a catastrophic loss of public trust the next time a real validated warning needed to be believed. It's also worth pausing on why forecasts like this land so hard with an audience, because understanding that is part of understanding the whole picture. Disasters create an immediate, powerful need for explanation, and when something as violent and disorienting as a magnitude of 7.4 earthquake hits, this was random and we currently can't predict it, is a deeply unsatisfying answer, even though it's the accurate one. A confident voice offering a clear causal chain, this triggered that, which loaded this, which set off this, feels like control being handed back to you in a moment defined by its total lack of control. That's a completely normal human response to uncertainty and fear, not a flaw in the audience. Livestream formats amplify this further. A running commentary, delivered in real time as videos and casualty figures roll in, with maps and technical-looking overlays pulled up live, carries an air of expertise and immediacy that a calm, hedged scientific statement almost never can. USGS publishing a probabilistic hazard statement in careful, qualified academic language is not going to outcompete a live stream that says, "I told you this would happen," while playing back an old clip as proof. That's not a reflection of which one is more accurate. It's a reflection of which format is built to be more compelling. And the incentive structure matters too. Content that makes big, specific-sounding claims about danger and prediction tends to draw more engagement, more shares, and, in monetized formats, more direct financial support in the moment of a crisis, when audiences are primed to want answers and to want to reward whoever seems to be providing them. The healthiest way to engage with this kind of content is to enjoy the parts that are genuinely educational, and there usually are some, since a lot of these creators do walk through real tools like moment tensor solutions and USGS shake maps, while staying skeptical of the predictive leaps layered on top. Real geophysics and unproven forecasting frequently get presented side by side, in the same tone of voice, using the same visual language, which makes them very hard to tell apart unless you already know where the line sits. Now you do. Here's what's genuinely useful, and doesn't require any speculative framework at all. Colombia, like much of the Pacific Rim, has real science-based seismic hazard maps built from decades of instrumented data and geological fieldwork. Those maps already told anyone paying attention that Western Colombia sits in one of the, OST seismically hazardous zones on the planet, full stop. Not because of a lunar transit or a geomagnetic storm, but because it sits directly on an active subduction zone that has produced some of the largest earthquakes ever recorded, including the 1906 Ecuador-Colombia earthquake, estimated around magnitude 8.8, one of the biggest earthquakes in the historical record anywhere on Earth. That's the real headline hazard information, and it's been publicly available for decades. This is a place where major earthquakes happen, current infrastructure has to be built to withstand them, and people who live there benefit enormously from concrete, actionable preparedness, not a vague 2-month window on when the next one might strike. That's also where the actual life-saving message in all of this lives, and it's worth spending real time on because it's the one part of this story that isn't up for debate. If you live in an earthquake-prone region, the things that meaningfully improve your odds are not about predicting the date. They're about being ready for the moment it happens, whenever that turns out to be. Know your building. If you're in an older structure or one you're unsure about, know the fastest way out, and know where the sturdiest cover is if you can't get out. Under a solid piece of furniture, against an interior wall, away from windows and anything that can fall. Drop, cover, and hold. On the instant shaking starts, don't wait to assess. Don't try to run down multiple flights of stairs mid-shake. That's when people get hurt, from falling debris or from the structure itself moving under them. Get low, protect your head and neck, and hold on to something stable until the shaking stops. Have a go bag ready, water, a first aid kit, any needed medications, a flashlight, copies of important documents, somewhere accessible at home and ideally at work. Know a meeting point for your family if phone networks go down, which they often do right after a major quake. And remember that danger doesn't end when the shaking stops. Aftershocks are extremely common after a quake this size, and buildings that were structurally weakened but still standing can come down afterward, sometimes minutes or hours later, as we tragically saw in some of the footage coming out of Colombia. Getting to open ground away from structures and staying alert for aftershocks matters just as much as the initial response. None of that requires believing in any prediction framework at all. It requires understanding hazard, not prophecy. And that distinction is really the whole point of this video. To bring this all the way back around, a real devastating magnitude. 7.4 earthquake struck Colombia at real depth with a real and understood tectonic mechanism, following a real and documented clue. Stir of large earthquakes across the Caribbean plate region over the preceding weeks. That part isn't in question, and it isn't oversold. It's a genuine tragedy, and the people affected deserve real support, not exploitation of the moment for engagement. What is in question is the leap from there's a documented regional pattern of seismic clustering, which is legitimate, if limited, science, to I predicted this specifically, and the official scientific establishment is lying to you about being able to do the same. That leap isn't supported by the tools being shown on screen when it's made. Moment tensor solutions, USGS shake maps, historical earthquake catalogs, those are real, and they're genuinely useful for understanding what happened after the fact. They are not, on their own, a validated predictive system, and presenting them as one, especially in the immediate aftermath of a disaster with real casualties, does a disservice to people trying to understand what's actually happening and what's actually worth worrying about next. If you take one thing away from this, the honest, unglamorous truth is that nobody currently knows how to reliably predict when and where the next major earthquake will strike. Not the forecasters claiming otherwise online, and not USGS either. And USGS says so plainly and publicly, not because they're hiding so me think better, but because that's genuinely where the science stands right now. What we do have is decades of solid hazard mapping that tells us where the dangerous zones are, and a well-understood, well-tested set of preparedness steps that make a real, measurable difference in outcomes when, not if, the next one hits. That's less exciting than a countdown to the next big one. It's also what's actually true, and it's what's actually going to help people who live in these regions make it through the next earthquake a little safer than they otherwise would have. One more thing worth saying plainly before we close out. None of this is an argument that curiosity about earthquake patterns is bad, or that ordinary people watching this kind of content are foolish for finding it compelling. Wanting to understand why the ground under an entire region seems to be waking up at once is a completely reasonable instinct. And some of the underlying questions, how connected are these fault systems really? Could better real-time monitoring eventually improve short-term forecasting? Is there anything to some of the more subtle environmental correlations that keep getting studied and restudied? Are genuinely open, genuinely interesting areas of ongoing research. The distinction that matters isn't between boring official science and exciting independent forecasting. It's between claims that have been tested against their own failures and claims that haven't. A real prediction system has to be right about the times nothing happens too, not just the times something did. That's the bar, and it's the same bar everyone's ideas should be held to. Professional seismologist or online forecaster alike. Stay safe out there, and if you're in an earthquake zone and don't have a go bag ready yet, that's genuinely the most useful thing you can do today.